Are we talking about with the banked curve? Are we talking about a bike, a car, a truck? What do we care? Okay. And it's going to be a banked curve? Yep. All right. All right. So if we've got a car going around a curve, okay, as you've already said, here's our car, okay, and we've got the centripetal force, centripetal, and you know, in this situation, FC is supplied by friction. Okay, so we're talking about a flat curve, a flat circle, right? So FC is supplied by friction. Now, so if we have a car moving around a circle, it's a flat circle, it's got centripetal force acting on it, its speed doesn't change, its velocity is changing at every single moment because its direction is changing at every single moment. The centripetal force is supplied by the friction between the wheels and the road. Your question, for if we were to transform this flat curve into a banked curve, what speed would we need to do to get, what angle would we need to make it such that it has no need for friction to go around the curve? All right, so let's look at that idea. Do we have a radius on the curve? 18 meters. All right. So here we have our car going around the curve. It's got a radius of the curve equal to 18 meters. And when we look at the car, we think to ourselves, it's got two forces acting on the car. Now, one force is downward here like this. This is the force due to gravity. And the other force, I've made it too big. Okay, the other force is the normal force acting up through the center of mass of the car at 90 degrees, thanks to the actual banked curve. What's the speed that we're traveling at? Okay, so velocity equals 24 kilometers per hour. Can you give that to me as meters per second? Divide by 6.67. Okay, so if we want this car to go around that curve without the need for friction, then we want there to be no force upwards. Force due to friction that way does not exist. No force downwards. Force due to friction that way does not exist. Okay, so there can only be the normal force directly up through the car. So what speed? Now, if that is the case, then if we're not supplying the centripetal force with friction, what are we supplying the centripetal force with? Correct. The net force between gravity and the normal force is supplying that. And the net force can be shown right here. So if we get the correct angle theta for a radius of curve 18 meters at a velocity of 6.67 meters per second, if we can get the correct angle theta, the net force will be horizontal towards the center of the curve. So we've got vector, net of the two vectors, but it makes a nice triangle. So yeah, so we could probably just put them together and say, okay, here's my force due to gravity. Here's my normal force. This is the net force there. We got this theta. Where would theta fit into this diagram? Opposite the net force. So down here, very good. Okay. So theta fits into there. That one there. Now, we know what the force due to gravity is. I mean, we know what mass of the vehicle is. We do. What is it? Okay, 1,250 kilos. So mass equals 1,250 kilograms, 1.25 ton. So we know that. We know the speed. We know the radius. So we can say, right, fantastic. We know this one, know this one. So we can say, right, tan theta equals the net force. The net force over the force due to gravity. Would you agree? Okay. So we can then say that you know, theta equals tan neg 1, the net force over the force due to gravity. which equals tan -1. What is the net force, out of curiosity? It's centripetal. Sorry? It's horizontal. It's centripetal. What's the equation for centripetal force? mv squared on r. So we can say, right, okay, mv squared on r. What's the force due to gravity? Yeah, so m times g. Okay, it's worth writing down because did we actually need to know the mass of the vehicle? No, we didn't, because this mass cancels out with that mass, and we find out that this equals tan -1 of v squared over gr. Just check my math, make sure I'm correct. You've got the velocity, you've got g is 9.8, and you've got the radius is 18. So that'll give you the theta that you need for that job to happen. So if you have a look here, v squared on r divided by g. Yeah. Now, you might remember in your old school days when you're doing math, you might remember that a on b divided by b on c, okay, that is equal to a on b multiplied by c on b. Yeah. Remember that? So if I have v squared on r equals divided by g, okay, that's actually g on 1. So it becomes 1 on g multiplied by v squared on r, so the g goes down there. All right, we good? Okay. So if we're thinking about an object that's just hanging there off of some cable, and the cable has an ability to supply a tension force to the object to counter gravity, and it might be that this is at T max for this particular object. And we ask the question, why is it that if we set this to swinging, if we set our object to swinging, that cable, which previously was strong enough to just hold it, if we set this to swinging, why is it that it will snap? Okay. Yeah, the tension required for that swinging motion will exceed T max, but can we show why? So if we look here, bringing a brick, good. That looks like a brick, doesn't it? No, not really, but it doesn't matter. So if we set this to swinging at this location here, T centripetal, so that centripetal force, well, no, that's wrong. At this location here, T is going to be greater than T max. We have to talk about why, all right? In this position, there are two forces acting on the brick, if we like, okay? There's a force of gravity pulling it down. There's the tension force pulling it up, and force due to gravity equals the tension force. In this location right here, the force of gravity is identical. That hasn't changed. But this is now going through centripetal motion. It's going through force. So is it, for this one, there is no acceleration. No acceleration. There is acceleration here. Which direction is the acceleration? Up. So we know that at this point here, there is a net acceleration up due to centripetal force. Yeah. Okay. We know that the tension has to overcome gravity, and then in addition to that, supply enough extra force to supply the net force. So now this tension here, we'll call it T2, is actually greater than T max. Okay, so we'd say, okay, right, fantastic. Net force equals T plus mg, okay? T equals net force subtract mg, okay? Which means that whereas previously at this one here, you know, net force because here, that is still true. Net force equals T plus mg, 0 equals T plus mg. So T equals mg. Here in this situation, T no longer equals mg. T equals this value, which is greater than mg. Okay, and so it's going to snap. Yes. 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 The student in the question just summarized this really, really well. The student said that due to the fact that we're moving in circular motion, the forces acting on the brick are no longer balanced. That's what the student said. Given the fact that the weight force doesn't change, the student said, well, therefore the tension force has to be bigger. And as a result, it's going to exceed the T max, which we previously identified. By saying it that way, they're actually saying it better than the way I said it originally. So that's pretty good. On the topic of Kepler's law, it was asked, do we need to worry about meters and seconds for the units in this, or can we use kilometers? Can we use hours, weeks, etc.? So if you're using Kepler's law as a whole, then yes, that needs to be meters, that needs to be in seconds. However, you recognize that for all the satellites about a central mass, and here you have satellite A, satellite B, the period squared over the r cubed for satellite A is equal to that. The period squared over r cubed for satellite B is equal to that. It's exactly the same. So you can say that the period squared over r cubed for A is equal to the period squared over r cubed for B. You don't actually need this part of it. When you put them together like that, if you choose to use kilometers here and kilometers here, hours here and hours here, days here and days there, those alternative versions of the units actually cancel each other out. So in that situation, you don't have to stick with meters and seconds. You can go kilometers,